Alright, so we're going to do concept designs in the shower before I go to do my laundry by having to ride my bike all the way over to my parents' house with the trailer that has flipped 3 times with my dog in it. Yay! Super! Along with 2 other times with just myself. That's nice. Super. I'm not afraid of it. You're afraid of it. Not to mention, it's genuinely like an hour there and back every time. Anyways, so I was thinking about manufacturing, things. I had an idea for a business if I could get investors involved to be able to make an increase. Basically, it's upgrade old engines into being something volumetrically more efficient, structurally more sound, and ultimately produce more power for the given amount of energy input, meaning, gas that's being used. So, which is energy, just is potential energy. People don't often think about it like that. They think about it more like, oh, it's gas, go burr, boom, boom. And I'm like, well, you are correct, Grug. That is correct in every way. I just extract boom energy. I go brrr with this around it, and it goes brrr over there. So, like, Grug is correct, everyone. Grug be smart this time. Grug is very smart. But gasoline is simply a potential energy battery. It's an exothermic potential energy battery. That's all gasoline is. You have to get the smart people to be entertained for a second. Stick around, maybe. Now, the manufacturing changes are kind of pretty similar. So, like, let's take a flathead V8 first. They're push rod. They have this thing that comes up, and they're all kind of out of whack. When you look at it, it's like they're not very good as an engine, right? Like, there's a reason why we moved from having the intake and exhaust right next to each other. Like, not to mention, there's a huge top part that massively reduces your compression, and then there's all this other stuff that's going along in a busy ass place, and it doesn't really have a way to like remove the heat hot spots. You know what I mean? At the top. That's why a lot of them have these heat sink fins, and they're usually steel or cast aluminum or something along those lines, right? To try and improve its thermodynamic efficiency and a reduction of possible, knock. So, a lot of flathead V8s could be improved dramatically with just the heads, but we're not going to go with the heads first. I get to the heads. I don't get to why the manufacturing of these things are really cheap, simple, and easy. Because I'm going to describe the process, and then you'll get to understanding why that process is doable for these things after I get to other processes that I'm doing it for elsewhere in the bottom end. Crankshaft area, specifically. So, we all know engines are improved by girdles, meaning strengthening areas in that, round rectangular part, depending on the engine. That's at the bottom where your, oil pan and so on is. So, flathead V8s have a nasty problem of only having 3 connection points to the crankshaft, often, So, well, if you hog out the area around there, you can effectively install a girdle that has 2 more connection points in that area, and that turns into stamped aluminum sheets. Okay? So they're going to be the right thickness, and if you look at, hold on. You look at anti-roll bars, they are hollow with an outer and inside diameter. they are sometimes aluminum. More than good enough to support the weight of a vehicle. And in fact, those are higher performance applications with the right aluminum. You know what I mean? They're lighter, they're stiffer, they're just strong enough. Good enough, right? Okay? So it's like, if you know what I'm talking about, then you know that that can be done. It's just the right sheets of aluminum. Thickness, gauge. So we're going to talk about how if you do this the right way, meaning you hog out, you carve in the right geometric cut, and then as you fold it onto itself, you can make a stamped part. If you heat it the right way, it becomes more pliable, more readily and willing to properly bend and join even. You can weld it if you put the right electricity through it. And because eddy currents are a bit of a dick to deal with, you know, for aluminum specifically, if you use electromagnetics, and let's say it was hyper-eutectic, it was silicon. Well, if I want to zap them and I use the right electromagnetic, kind of like I'm trying to do an induction in a mandrel bending style as it extends out and then folds in to gain the non-shear forces and crimp forces into the given sheets of aluminum, then you'll gain an advantage in cost to outright effectiveness and very small amounts of necessary slow but steady bends. You do it in an airless vacuum environment, and you cool it off with nitrogen, only nitrogen, and you force an inductive current with a aligning of a eddy current and electromagnetic current, meaning field really, not current. Then you'll be able to gain a directed area with grounding for the welding of the aluminum girdle. As a result of this, you can very quickly bend and slap together a sheet steel, or sheet aluminum in this case, because apparently you keep going to sheet steel over and over and over. Remember, it's sheet aluminum. Sheet aluminum is what we're dealing with. Same thing with, like, I can very quickly make an oil pan that's effectively a version of that. Like, I can just burn, boom, and it's just rounded instead of needing to shear it, you know, like bend it the right way. So, like, that makes it totally easier. In a lot of ways, yeah, it's way easier. So it's like, well, that's a part of the girdle, you know, and you're going to bolt that together. So you're going to make sure you drill and thread the bottom. But hold your horses, we're not done yet. So we got 2 extra connecting points. It's aluminum, but we can put in the steel bearings that are necessary. You know, chromoly, whatever it is, right? For your crankshaft to ultimately rest inside. Now, those are great, and that would significantly reduce the bottom end and strengthen it, okay? Reduce the bottom end's weight and overall size, you know, the complexity there, right? But we're not done yet. So we're going to hog out the front, the sides, and the rear in a geometric pattern, kind of like they do with the diamonding pattern on bell ends for rockets, where they reduce the weight, but they increase the strength and the rigidity in the area that is necessary for the given applications, tensile, compression, and other loads. It also helps to reduce some of the heat and dissipate it. So if you do that the right way, you can structurally support the block better, but also reduce its weight. It's not a very easy thing to cast that, but when you're upgrading this, that makes sense to do. And it would be something that for a flathead V8, it would just be a given mock-up model that you would then plug into possibly a CNC, or, in my mind, this would be something a little different. It would be a just like literally it's just a machine to hog out that area. For what it's worth, it's like, well, I don't need a CNC because I don't need to plug in every single solitary given version of this vehicle. Like, or its engine. This version is, of its engine. Like, I don't want to do that. Like, plus those are expensive and I don't like it. So, brute force and then clean up touch-up work, which is the next machine. It's like, basically there's 2 to 3 machines depending on what you're going to do. So, like, you would essentially just hog it in with one thing that's just going to just drum, like a drum, you know what I mean? That's just going to, like, go over it and then hog it in and then take out that material, and then you'll get the next one, which effectively just cleans up those areas and adds a little bit of those circular areas, like a dome has a circle in the center to improve its structural support. Alright, same kind of deal. And then we hog out the center, which used to be where the, hold your horses, camshaft is. Well, the camshaft's come on. I'll get to it with the heads. Well, the camshaft is going to be hogged out, and we're going to place in another aluminum stamped sheet metal that's welded and formed into being a supportive member with the right, hogging out, meaning dovetailing or other versions of that we press fit it in, and then we bolt and effectively try and weld, which steel and aluminum don't weld very well together, so it's usually just bolts and like proper press fit in, hard to remove areas that are bolted together, that kind of thing. Right, and you have to do it in several sections, making it easier because you don't have to press fit in as much, and the material will break if you try and do that, and so you basically make a suspension bridge kind of between the two, which reduces its weight and increases its structural stability, front, rear, and side to side. Now, the inside of the cylinders are to be bored out and then honed and then turned into a powder coating of incredibly hard ceramic. We want very hard ceramics, not steels, ceramics. We want to bake it. We want to make the inside of the cylinder extremely non-porous and hard, and as a result, less friction, improved efficiency. It's still thermodynamically very good because it's a thin degree of this ceramic, and as a result, it's thermally conductive, more than good enough, with an incredibly reduced frictional capacity. Now, the heads. The heads are just a one stamped steel and or aluminum, depending on what you want. Okay, I was going to go with steel because it's easier and it's cheaper, and it's cutting it out. Instead of eddy currents, we actually use a forging/tempering process that aligns, as we're cooling it, the given crystalline structures to improve its stiffness and its given flexibility for its, forging and then quenching style that's going on. Alright. Now, it's static and current to weld in that area, but the difference is there's a sliding valve instead of the sides valve on the inside. So kind of like the side valve of like a 2-stroke engine. Well, the valve is going to slide on a ring. You know what I mean? But instead of it being a connected ring, you don't have to do that, but it's much closer to where the cylinder is, and then it can be sealed using its own version of piston rings, where it's down and then over and then down and then over and down and over, and it can still have its own bath of oil, and it's still got coolant right next to it to cool it, and oil return. All of it works. Now, that allows for an increased degree of compression. The intake's on the inside and the exhaust is going to be on the outside. The valve is placed inside first, and then the camshaft is on the top, and it presses a hydraulic ram plunger. One side opens it, and we use solenoids to lift it up and push it forward and backwards. So up and down, forward and backwards. That gives you lift, duration, and that's about it with timing. You know what I mean? Now it's a standard camshaft, but you can change its degree of lift and duration too, and you can change that pretty quickly and keep it there for what it's worth for those solenoids. Now, as a return hydraulic ram, as you press it, it returns it to close it. And it's sealed enough to where the compression's still there, and the degree of increased thermodynamic efficiency and ultimate capture of energy is now improved. And then exhaust goes on the outside. Standard outside exhaust. Inside intake, exhaust outside. Exhaust can also be changed to have scavenging effects at higher RPMs, or with that solenoid and change. You only need one camshaft for the intake and exhaust. But depending on how you move those solenoids, you can start the intake process while the exhaust is still going on, and you can get my two-stroke style where middle dead center is going to be your new exhaust bottom dead center. And then you can have scavenging as it exhausts and gets to the point where, oh, well, it's lower enough pressure that intake can come in and it can ultimately push out the exhaust closes, you have intake still coming in, and you can gain a two-stroke advantage, which is great. And that's the old part. It's like, well, I'm going to drill and tap, and then like that's stamped steel, which is effectively all it is, stamped sheet steel, that's pressed fit and then welded together, and then we're going to coat that just a little bit with the ceramic, because I want to make sure the sliding valve is very, very lubricated. So it's going to move faster, and it doesn't have the oil getting into the channels by having a T and its own version of grooves where it sits into and is pressed into and has gaskets in it, basically. It has a seal, so it's like the gaskets still fit. Right. So as a result, that improves its degree of compression and sealing, while improving its volumetric efficiency. It improves its degree of knock, because I still have those heads to be able to return those oils and coolant back into the oil pan sump area and the radiator respectively. So it's a way to upgrade old engines, and I feel like this is a cheaper method in all aspects because it's fast, efficient, press it in, get it done, push it out, and it's a way to make old junkyard, you would never even think about using the engines into something that with the right, plugs, the right, like rods that have the right holes, to seal up any possible rust damage, and effectively make them structurally sound and now viable, that I don't have to waste as much energy, because the energy grid is currently suffering quite a bit. And then same thing with resource management. It's like, well, I don't want to go buy all these resources. and or even recycle the ones that are there. This is a way to recycle and upgrade them and recycle them at the same time. Upcycle those engines. Now they're old and they're heavy. Well, this is a way to hog out some of that. This is a way to also gather some of that steel, iron, and other material for aluminum back, while giving those engines a new breath of life that are now high-performance engines or regular everyday car engines that can be stated that they are environmentally friendly than trying to produce these batteries and electromagnetic motors, which take a lot of energy and they take a lot of resources that you have to get from somewhere that often, more likely than not, comes at a human cost. And so we already have a lot of this just sitting around in junkyards doing nothing, and a lot of these ceramics already exist. I don't need to get a whole bunch of new material for the ceramics, and they can be conductive because I can hog out the inside around these iron blocks, which before they didn't have like a full jacket to cool them. Well, now they're going to have a full jacket to cool them. You know what I mean? Like, they're going to have the right structural supports, and now they're going to be able to be far more viable as a new performance-minded engine to regular consumer-minded engine. And the reason why I was thinking about it is because, well, there's a lot of cost associated with all these things for renewables. And I like renewables. I want renewables. For anyone out there that doesn't know, I prefer renewables. Because the infrastructure is not currently there. There's a lot of pushback. And for what it's worth, this is a way to transition older style vehicle engines and or current on-the-road engines into more performance efficiency engine styles that allow for us to gain a reduction in overall fuel consumption, both to our energy infrastructure and vehicles on the road, while we transition. That way it's more feasible to allow for a carbon sinking during the transition. Despite everything, constantly buying your way out of the problem is not really as, good as people think it is. Buying a bunch of new cars, buying that, like they say vote with your wallets, but really that takes energy. It takes energy overhead. It takes a lot of resources. It takes a lot. And so this is a way to make it so that's done with this. Like, it takes a while to do that. Well, this will allow for that to be done much more easily. Those resources can be diverted that are taken off to making renewables. Now we got a bunch of, cast iron and steel and, aluminum and so on. That's good. We want that. We got old engines that are a breath of fresh air, for what it's worth. We can add in better, more efficient sliding valves or degrees of poppet valves. They use a lot of poppet valves. I'm not a big fan of poppet valves. Personally, I can cool sliding valves just fine. In fact, I have a version of a turbine style, and it's a sliding valve. It's a version where it sits at the top in its own little cradle kind of thing, and it slides. It has two counter-rotating slides. So, yeah, they're plates that slide. As they counter-rotate with the right, connected axle and gear on the outside, then I'm able to slide them with hydraulic fluid or just regular as engine oil, and turn them with a hydraulic fluid that spins them. You know what I mean? As they go from one side, they spin around and they go backwards. That gives you the ability to change how they perform in terms of timing, and that's about it. For what it's worth, I don't really need much more. Like, they're full open, full closed, kind of a deal. But then, for what it's worth, I'm using a degree of air, okay, which means like there's this pressure, this exhaust, this amount of fuel, and it starts to turn a little bit more into like a diesel, where it's like the amount of fuel I'm putting in and the leanness of the mixture, and then there's a whole bunch of other stuff with exhaust, which I don't want to get into. But like for just regular heads, which I can change, like it's degree of so it wouldn't be lift anymore, it'd be really the wideness of its opening, but that would have its own version of another 2-pack of spinning plates that you would control dynamically to be able to change its degree of opening and the amount of time it has. This one's a real simplistic one where it's just like, well, you'll get opening completely. You'll get, you know, it's slowly opening. You can have scavenging effects depending on the timing. All right, and you'll get like a version of the 2-stroking if you want that. All right, so that's good. Now, where the spark plugs go into, they go through the shaft. Same thing with a fluid, which is your gas, which is going to have a pump, you know, which is a gear-driven pump that goes down and up. So as it pushes down, during its pressurization, it's like a direct injector. But I don't always need that because, like, the electrode, I used a version of sucking out electrons, and so I turned in the air and fuel, which is in there, which at that point you compressed. I used like a bowl of like a bunch of electrodes, and effectively a bunch of electrodes and ground. So through the ground, I suck a lot of electricity through, and then pull electrons off of that already very, very compressed and hot air and fuel that's in that little ball, and then I fire in your gas, like a small amount, which essentially atomizes and plasmifies the gas and air and fires it in under extreme high pressure, which then, of course, allows for a very, very, very efficient, incredibly fast burn to not as fast, depending on how you want to play it and the pressure that you're going to use, because it can spread throughout the entire combustion chamber very quickly, as it is negatively charged, and the air and gas usually often has a acidic charge, meaning it has a positive charge, which increases your exothermics for what it's worth, you know, advantage-wise. So, as a result of doing that, I gain a fairly significant degree of outright performance. Now, of course, I have to have a different style of spark plug. They're built into the head now. They'll last for a very, very long time, for what it's worth. And yes, you can screw them in, but at the same time, it's not really something I would think you could probably break out very easily, you know? So, that's like one of those, well, yeah, no, I mean, I suppose you could do that, but, you know, realistically, you'll probably just replace the stamped aluminum heads that have ceramic on it, yeah, so that way they're stiffer, and they're thinner, and they're lighter, that allow for, like, the turbine style, you know, camshaft at that point, which rotates these valves, which gives you your higher degree of, you know, continuation of valves, you know, clearance. Effectively, there is no clearance issues anymore. There's no such thing as an interference problem, and it's about timing then. And so when it comes down to like how you allow it to slip and how you allow for it to start, you know, the exhaust process, then you gain a degree of precision, you know, and so that'll still slide and not allow for any exhaust to come out, okay? And it's still got compression going on during that moment. And then it'll start a small amount of opening. As it slides, it'll fully open. But that, hotter part will go into the cooling jacket and effectively cool itself as it slides over to the intake. Which the intake has a port, which is a vortex inducer. Okay, so it's a vortex where you place in your injector, and then that uses a super nozzle. Effectively, it's a nozzle that has this size that then opens up, and then it'll turn into like a double raindrop. So it goes from a small point to a wider point, and then back to a smaller point. But then there's a bunch of little nozzles there that spray an atomized, or more specifically, very fine mist into the port, right above where the valve is. And then you still have the ability to press in fuel without putting the plasma through for the direct injection. So you can get really good results with a head like that are very cleanly burned, which is nice, and reduce nitric oxide for leaner burns and carbon monoxides for what it's worth. Which, that's because of the plasmification. Yeah. And that's the reason why it works so dang well. That, and I have a whole bunch of other stuff for the intake area with the double fluting, which I've talked about. And then a RAM. Oh, I created a better RAM air compressor. Give me a second. Really? Yeah, I was like, well, RAM air, and then it's just bifurcating. If you don't know, it's a parabolic funnel that, you can bifurcate it at certain, areas and junctions. So that if you put in fluting, and in between the fluting, or not fluting, but channeling. So it's there's grooves in it that are straight line. They're not curved or anything. And then where those grooves are, you're going to stick out another part that's going to bifurcate that air and try and separate it. And then you have a center part that's there, okay, in the rear that's going to stick up towards roughly around where the middle is. Now, they have to be properly machined, which usually just means casting. For what it's worth, I actually don't even use casting. If you want to know, I just use stamping and then rolling, like extrusion of aluminum, where it's I'll stamp the aluminum and then I'll roll it into having the right bumps and grooves, and then I just weld the thing together once it's the right shape and size, and so that way it allows for the right degree of separation and channeling and all the rest of it. So that also have the outside that's there, that it bifurcates with those little whale bumps and then the channeling and grooving. But the fan is rather interesting. So the fan in the center is vastly different than others. It takes an outside from the outside shroud in, an inside out, but downward approach with another version of a parabolic funnel that combines that and then realigns it to be a version of a parabolic funnel laminar flower. Okay, you have to have it laminar flow. Then it goes into a air-to-air, which there's a water-to-air exchanger because I have a bunch of hollow areas in the aluminum that I rolled and everything. So it's that's a bunch of surface area. That's a water-to-air as it's coming in, and I have to go from wider to smaller anyways. So that's perfect for condensing using a water-to-air, And that also helps with compression, using thermal reasons versus mechanical reasons to compress it. Which it uses mechanical as you're pushing through the air, but you're also cooling it using water to air, which condenses the air, which compresses the air, but also speeds up the air. Then it goes into the, so it's a bunch of little tiny, not tiny, but, blades. They're kind of like a front part of a turbine, but they have little holes in them, so wait, that are elliptical that go from wider to smaller and are curved in a particular way to try and grab the air, stall the air, and then create little vacuum areas that suck them further down, kind of like a Tesla valve. You know, where they rotate, but then they're going to drain that energy into. Well, because it's spinning anyways, I'm already going to use the energy, so it's like whatever. You know what I mean? But that's what I basically use, and then it goes from the outside towards the center, which they're mostly just scoops, kind of like spoon stuff, that are really just really close together. And they have those little blades at the top. They grab it, and then they suck it, and then they have the right fullering and channeling. No holes in this one that allow for it to get scooped towards the center, which the center has a hub that is going to go up towards the center, and it's like a standard centrifugal compressor, but instead of that version, we're going to use something a little cooler. So it's another one of those little blades that are very tightly, you know, because the trailing part of that bottom third for the ram air bifurcation cooling thing happens to be, you know, kind of like the wavy guide styles on a, you know, jet engine. Well, these have to get into that, and that helps with sealing, and we want to always have like a little bit of that next blade ready to grab that little air that's going to pocket for a second after it goes off and through that next one, which grabs it and sends it down. So there's already some going down, which produces a degree of, hey, I have an empty spot. There's a lower pressure, and then the blade comes around and it scoops more and it pushes it down, and so it's always doing that. With a degree of some of those air holes that allow for it to keep doing that as it spins, reducing its overhead pressure buildup in between so I can get tighter tolerances and gaps. With stiffness, because if you don't know, it becomes more stiff when you have holes like that, and it becomes more rigid and more able to handle higher pressures and speeds, centrifugal. Anyways, instead of a scoop version though, it goes downwards, it goes two channels that are there to like basically bifurcate it, so a bunch of teardrop shaped kind of channels and columns, kind of like the centrifugal that I was talking about, except it's got holes on the leading, in between the leading edge, so that way as one side gets too much pressure and it basically balances and oscillates pressure waves as it spins, and then it captures it into the bifurcation as it goes over, diffuses with the next onrush of air, helping push it down very cleanly, then takes that volume and then splits it into a smaller volume. So we go from a larger to a smaller, all right? And then that goes off towards the outer, towards the center, which is these little holes with little versions of scoops, little scoops slash stator slash, you know, kind of directed downward blades. Very high angle versus low angle, very flat, you know, that kind of thing. So that way it grabs it, and as it spins, it'll grab it and then suck it down by producing a degree of vacuum that's moving around. Okay, so those also have holes, and they also have channels, all right, but then they also have little bumps for the given angle. So that way it sucks it through and it directs it down. And then we have the next fullering and bifurcations, which is like bifurcating to bifurcate at in the middle for the ram here. And then, but this one's more specifically to slowly curve that angle and then direct it towards its center, and it goes from a wider to a smaller, and then a bunch of little stators essentially that are going to just try and direct it in a laminearistic approach. Very high pressure, very high flow rate now. That are actually smaller at the top and then wider at the bottom, so that way they're stiffer, but also they compress it more because there's more space there in between where it's getting sent out. Now we're going to get to the air-to-air it still goes into, because like the ram air and the bottom ram air are still water-to-air cooled with a jacket, which is in a jacket. It's really the stators and the, yeah, so it's like all of that's cooled while it's getting compressed still, And the coldest side is at the bottom versus the top. You know, which is like, how did you do that? I don't know. There's these connection points between the outside and inside, and it's hollow. So I felt like that's easy to do. Maybe you can do that, perhaps, because it's not solid. It's hollow. Anyways, so then we're going to get into like the air-to-air, which is a from either top or bottom, or if you want to do it side, it has to curve with those grooves and stators to try and go and diffuse to the full top and bottom of the air-to-air exchanger. But I usually went from a top-down approach or a bottom-up approach, because that's pretty easy to do. And then it's like, these are really wide mouth areas, you know, okay, that have like little vapor chambers that are teardropped inside of them, that then also go to the fins on the outside, which are, you know, directed with the wind, meaning on to it, not horizontal flat, or, well, they are, some of them, but, you know, they're going to be vertical, but they're going to be horizontal opposed with verticals that are within the side of the tube, teardrop again, hollow vapor chambers that then switch on the outside housing into being in flow because they're hollow. I just need them to be, you know, able to have the hole be there. It doesn't matter what the hole shape is on the inside, so long as the air flowing through is not as pressurized and disturbed and slowed down. Okay, so anyways, it goes up to the top. They go from a wider bowl to a smaller bowl, but then they bifurcate with multiple different little smaller bowls as it cools off, and it uses the fin density and the shrinkage into a smaller degree of intake, because that one's like, well, you know, let's say 5 inches as it's coming in. Well, then it goes and gets spread out with that, and then it goes down into like a 3 inches. So it's another version of a compressor using cooling to do it, you know, down to atmospheric is what we're looking for. So they'll go into a smaller, you know, kind of like teardrop, I guess, shape, you know, hollow that then goes all the way to the outside with a few stators that are there on the inside of the triangle pyramid from a rectangle to a small spot that goes into the 3 inches or whatever size tubing diameter. Well, that goes into a 1.5 inch intake manifold. That's really just the intake double flute system. Here are 2 parabolic funnels. Well, they have fullering, and then like the tube is multiple sections that you clamp together, which have, wait for it, more fullering, more channeling, more grooving. And so they are curved towards the inside. So it goes straight dead on at the front, and then it goes from the top or the bottom only at the rear. And what that does is it curves the air towards the center from the rear, and it gives it a massive Lindenbaum, yeah. And it makes the rush of air more statically pressurized. Okay? Now, the grooving on the inside of the tube is such that it scoops air towards the center from the rear and the front. And the center is very much just channels, meaning fullers that have little channels cut along the side. So that way they'll weave in between and stall and create some vortex around there. So they'll try and head downwards, and that increases pressure up there. Now, on the where the flute is, all right, so it's a standard parabolic funnel, like a hypervelocity stack, that takes little flanges. I call them flanges, but they're really just a piece that's got some slots in it, with on the slot sides that are solid, some little holes that are elliptical that try and direct some of the air down. So it stalls the air, directs the air down as it tries to follow the curve. But what they're there for, on the pressure coming out, it directs it back towards the center, with the rear towards the center again. Now the double part is the big enchilada machismo part. That slots in, it's wider than the smaller one, which for what it's worth, it's still going to be roughly the same size. It's just that they have like grooves cut in that are countered downwards, or not countered, but angled downwards, that are there to help the rotation, which is going to be caused. So we have stators, they're not really the kind of stators that you think. As air comes in, looking at it dead on, it looks like air is just going to go right through. It's like it's not even there. Okay? But with the right holes and the right shape for the teardrop that those stators are, what it does is as pressure comes back out, it creates a pocket of a dead zone and a high pressure zone, which causes it to spin as it comes back out, going into the outer parabolic funnel fluids. And then it traps the majority into the inside area in between the inner and outer. And so it spins and it creates a lot of pressure there. But the inside funnel has a degree of slotting that is just straight. And what it does on the outside part is it helps continue its curve. And so as it pushes air through, as the pressure is wider, as it spins, it takes longer to get there. Well, the smaller inside, just still kept going in, will then get sucked outwards and then cause the spin into those trapped areas, and then the next pressure wave will join it and cause that to spin. As a result, I increase static pressure around where the ports are. I make it more consistent during its initial pull and after. And so it's like a ram air that's very, very good. Like I can keep it around 10 psi if I have 10 psi coming for a fairly long time without needing to worry about like oscillations. Like oscillations are very taken care of. As that air pressure that will come up, it'll still head towards the center with both the front and the rear pushing that air towards the center. So it maintains its static pressure given all the RPMs you can run at. Far easier and better. The exhaust is a different thing, because it's like, well, if I run essentially that plasma, I can run really lean with the port, and so the port then creates a degree of increased heat, and then I can pump in more fuel because I can run higher degrees of air. And then as the air and fuel mix and then push down from the initial movement of the piston connecting rod from top dead center over to like 11, 10, or I mean not 11 or 10, 1, 2, or 3, that gives me I can push in more fuel and it'll sustain its pressure for longer without having to increase top dead center pressures, because they're not all at top dead center. They're no longer at top dead center as I'm injecting. But the injector, which is a spinning ring kind of donut that goes up and down, and so as it pushes down, it pushes in. As it pushes up, it also pushes fuel in, making it much more efficient. As it spins, it also increases flow as it sucks more air, not air, but you can put air in it for what it's worth, but I just push fuel. Alright? But there's already air in the system. And while it was running lean before, well now it's no longer, and I can hit closer to those air-fuel ratios. Before, that would detonate. Now, they're not detonating. And I gained a much greater increase of sustained pressures, which increases torque, which also improves the NOx emissions and carbon monoxide emissions, while improving its outright performance. Now, as it goes to the exhaust, that is an entirely other thing, which is quite a bit different, I'll say. Let me say it. It's valved, yeah. Now, the valving is a teardrop-shaped valving, double teardrop, with fluting, or channeling, depending on your tape. It's a straight line in the rear. Alright. I use a electrolysis reaction. Or not really electrolysis, but I use electricity in the gap. So as air goes from its perspective of slightly faster, but it's not more compressed. Alright, but what it does is it produces a lower pressure zone into the divot. Well, that divot means spark gaps available. And it also means heavier, non-combusted particle with air, like a carburetor setup, as it goes through from a equaling tube header into one turbine setup for the turbo compressor. Give me a second. It allows for a breakdown of particulate matter, like a catalytic converter, using electricity. And the heat and the speed and pressure and torsional forces that are there to do it. It also burns a little bit of it, but then it goes into a turbine, which of course is a totally different turbine than most people are normally like aware of. It's like a short little stubby, like 5 inches, length, 5 inches. Like it's a square kind of like thing. But it goes from a short, small nose to a big, wide body that's going to extend for a little bit, and then it's going to drop down a little, but not much, into the catalytic converter. And so, for the pressure that's there, as I'm effectively going to add in these valves, which reduce the vacuum and the scavenging effect, except for when you want it to be there, because it uses the pressure of the exhaust to be equalized to a degree. There's a degree of back pressure, but then, give me a second. It's more like a Tesla valve, for what it's worth. It allows for straight flow, and there's a degree of resistance going back the other way. And it improves the overall vacuuming effect after the valve, and so a degree for the area after before the valve and after the valve that's inside the cylinder means it improves that pressure's efficiency. It maintains a similar degree of vacuum pressure consistently as it goes through, because it's not going to go backwards. The pressure is captured and then reflected off, and then with the spark gap, it's sent back towards the turbine. Alright, now the heating effect from the electricity that we're using is negligible. It's not really that much. It's really the exothermic that might exist there, but it's mostly about reducing nitric oxides and carbon monoxides and a separation that occurs during that moment of a depressurization crash out from hotter, more gaseous compounds versus more solid particulate that gets burned with air pressure that is there, okay, that's inside the valve, because it has to be connected in several spots. And you have a compressor, so a small amount is diverted to the valving area, which improves its efficiency as air both wicks and pressurizes into that system. There's a low pressure and it pushes in at higher pressure with nozzles. Yep. And as it moves outwards, because it moves with the pressure there inside of it, maintained with what is effectively a scuba gear equipment. It's a pressure regulator and flow regulator. And as a result of that, it improves the basic bitch version of, vacuum effects, scavenging effects for the intake for my two-stroke design, while it's also vacuum insulated. So, anyways, it uses slight reflective material and, electrically conductive material to improve the heating, but also the spark gap in from the ground that is the valve and the excited. Well, it's really, you can do either way, anode cathode thing, so it's not really that big of a deal for what it's worth to like really kind of think about it. But what it does not just improves the efficiency of the turbine, because the turbine has pulses that are coming in, which pulses aren't really super efficient for turbine. It tends to prefer, constant streaming of pressure. Okay? A never-ending amount of pressure. That kind of thing. Well, you can't really get that with a piston engine, so a way to get around that is by using the suctioning of other, which there's still a degree of low pressure air inside that cylinder, which is in the exhaust manifold. Alright? Now, because of that, it then will open the other valves and suck those valves too. Now, it also keep pressure pushing through from the compressor as a result of this, as there's always a little bit that'll come out, but it'll go back to being sealed and not coming out. Phaser, no, I gotta put these socks on. Could you please not? Gotta get the laundry done. Dang dog. Alright, you're getting way too aggressive. You go outside more often. Having trouble and a lot of pain after going on hikes. My physical therapy still hasn't happened. Phaser, stop. Alright, you know what? I'll just go back into the bathroom. Let's get this done. Close the door. Dang dog. Anyways. Yeah. Hey, don't open that door. Keep that door closed, damn it. Dog. Alright. So, anyways, it continues to allow for pressure to be sent into the turbine. Now, when I give up for the compressor, having its maintenance of continual pressure for the intake, I also make up for it with the intake manifold and the air-to-air and water-to-air exchanger for cooling and ramming air very efficiently into that with only one real fan. So let's see here. Those valves work a little, but they're not really meant for anything other than maintaining the pressure for the given diameter and size of the exhaust manifold. Okay? So that way it improves its torque and horsepower together. Now, the turbine is a different type of turbine. It's a needing to create with sealing for angled blades that create a very, very low pressure zone, and then it sucks out air from the front, and as it uses that suck out, it then counter rotates, because those are stators there. Okay? So those are stators that are sealing up to where the hub is. Alright? And so because it does that, it makes a near perfect vacuum behind, and then a very high pressured system in the front, of the exhaust gases. But then it has to go from up, then back down, and it goes up, and it has to counter rotate, because that actually improves its efficiency of continuing the vacuum, because it sucks it out. And so it skips out, and it has to be the specific tolerances between stator and the blades, and then it will take a much longer, more circuitous route around and diffuses itself from smaller little blades that then create this effect to the bigger blades in the rear that sustain it, and then slightly smaller in the final rear, and then that goes back into just equal, faster flow that's lower pressure in the rear than the front, making the high pressure turbine more efficient. Now, the stators then connect to the hub, which allows for a ring, gear that you can then put into the axle or fluid
depending on what you want to do, and then allow for that to head over to the turbo, which is also a supercharger because I tend to do super turbos, where I'll run a clutch-driven or electronic solenoid at certain RPMs where it'll turn off and the turbo takes over from the turbine. Okay, now this instead uses electricity production, like Formula One style MGU-Ks, because that's what's going to allow for that RPM to be matched for the given flow rate and compression of the turbo that I want to be at. Instead of wastegates, I don't want wastegates. I want it to maintain. But, still it might go over at different speeds. That's kind of what that is. And so there is still a wastegate, but it dumps it into the valve area, which is kind of like a pressurized cylinder rail, sort of. It's that kind of thing where it'll just dump it in for a wastegate into the turbine, or it'll dump it into the valve area. But that way it always has air going in, even when you let off the throttle, and it improves the efficiency of the turbo and turbine. Now that goes off into what I like, because I hate rare earth metals. They're super expensive, and people are trying to steal them for catalytic converters. So I use ceramic static charges, and the heat, because I didn't remove a lot of the heat from the turbine. It still removes some, but it's not that much. There's a vacuum there, and they're very highly insulated materials with vacuum insulation being there as well. And they're hollow blades to reduce their overall weight. But it improves stiffness and reduction of creep, meaning tighter tolerances for cheaper material with ceramics and metals combined. So as a result, I'm able to put a jacket around that, which is going to make a oscillating Stirling engine. Now the ceramic, and it's really just ceramic. If I'm being really honest, there's very little metal in there. It's just using static ionicking and systems that are very high flow. So it's it comes out, might come in at maybe let's say 2 inches. It'll leave at 5, that kind of thing. So it's a very big catalytic converter, but it's a bunch of ceramic, and it uses electricity because you'll have an alternator for your engine, but you'll also happen to have the heating and cooling effect that is the Stirling. So the Stirling has little heat sink thermal siphon, and it'll have a shroud over it to help improve its airflow, alongside of a little bit of diversion of air from the compressor into that, should it be necessary, because I was informed that that might be the case. Okay, with my mind thing, and people that would work with me to then maybe want to improve its reliability. I mean, any amount of air would probably help that, but it's another version of wider to smaller to improve velocity and flow characteristics. Bernoulli's, Venturi, depending, because they're kind of the same for what it's worth. I didn't ever really look that up, but they're actually sort of similar. They're almost just carbon copies. Anyways, moving on. It turns into, so that allows for a hot side, which is the catalytic converter, mostly. It's mostly the catalytic converter that's getting a lot of heat. Then we use static charge and electromagnetic. So pole alignment, and then we align the static charge differences, and then we use reflective material in there to make a resonance frequency of certain IR, microwave, light that will help break down the chemical structures far more efficiently, using the heat that's there and the electricity that we can provide it, and ultimately it makes a much cleaner design, because I can then make an electron flow battery between the static charge, the catalytic converter, and the various other parts for the negative side of my, what's it called again? Right, the electrode, the plasma generator, inside the cylinder, which is like a decent electron flow battery, but it's just meant to improve for the efficiency that's there, for the heat that's there, and I need to capture it anyways. I want it to not be super, like, annoying to have to deal with. Well, I might as well use that heat energy and electricity and some of the other stuff that we've learned as scientists and engineers to the best effect and advantage that we can to reduce carbon dioxide, monoxide, and nitric oxide emissions by essentially removing them. And by essentially I mean it's a percent of a percent now that we're at. A percent of a percent is really actually what it really is. Now, the reason why that works so darn well is just physics. So apparently, when they're quite hot, these gases, and you turn them into a plasma, like that already tries to produce a separation of carbon and oxygen. Like significantly so much so that should you have the right static charges, you'll gain a complete separation of the two. Now, it's usually unviable, meaning it takes so much energy that it's not worth it. But if we're going to capture that energy for a moving vehicle, it's already quite hot, and I only need to, for little small areas, to produce a slight degree of plasmification and ionicking to rip them out, and then I can have that carbon reconstitute as graphite, and then drop off into a can, which you can do. Then I have a carbon capture. Now the nitrogen's is similar, where it turns into N2s and N3s, and then O2s is what you get. Now it's quite hot, and we're using a great degree of surface area and degrees of help from electricity from the Stirling engine oscillation design and the ceramics and the materials that are there, with the reflective material producing a laser and electromagnetic pole alignment on the way in to the plasmification, and then the light helping align during the static charge different forces after plasmification, then improves the efficiency and recombination by separating like a centrifugal or just basic filter effectively that are for the oxygens and carbons, and so the carbons will drop off into their own areas, and they often will be cooled by that point because of the Stirling engine that's there. And as a result, I gain a crash out of graphite and N2s and N3s with mostly oxygens. Now, I could have that energy that's wasted turn into more electricity for a electric motor or something. Well, there's actually a fair amount of energy on the table for what it's worth. It depends on your outright speed and RPM of the engine. Right. But it's a very efficient system that only needs it to be run somewhat to reduce dramatically the amount, with a huge reduction in, well, actually there are no rare earth metals. There really isn't. But that dramatically decreases its overall weight, size, and complexity. The big downside is it means all engines have to be retrofitted or upgraded or upcycled with this technology to basically run far cleaner. And the graphite that you get are graphite nanoparticles, like really fine graphite nanoparticles, like super fine graphite nanoparticles. And there are no graphenes. So as much as people want there to be graphenes, sorry, this is not a way to produce graphene. No graphene is produced. Can't be produced this way. There might be a way. that's similar to using this technology, but for what it's worth, it's just going to produce graphite. I'm not trying to give you, the whole 9-yard spiel, but it's a bunch of chemical, ionic, potentiation essentially, and a very specific process that if it's done somewhere else and it's already known somewhere else, then that's what that process is. I call it the Lemke process because I came up with it and I have no idea what it is. So that's me. That's why I call it that. And now that means that it happens to produce a fair degree of excess energy. Heat. And there's heat recombination. It doesn't give you the same exothermic heat as like an actual like gasoline or something. You don't get more out of it. That's what I'm trying to tell people for the graphite recombination and everything. In fact, you lose heat because you're using heat and cooling to make that occur. So it's really just a really simplistic model of how to reduce our carbon into the atmosphere. It still comes out. For what it's worth, there's still carbon dioxides. For what it's worth, there's still going to be some graphites that are missed by the catch can. It's going to do that. But it's a significant reduction, like over 99% reduction for the given energy that's input to do it. And we're capturing the vast majority of the energy to do it. It's using passive instead of active. That's the reason why people don't understand what this is. A lot of people are like, well, this is active. You're using lasers. It's like, well, no, I'm using reflective materials that specifically make constructive and destructive interferences to amplify certain given light with the materials that are there, with the separation of different charge fields in very specific areas, with a massive electron reduction ripping out during heat, which creates a degree of plasma that then uses as a charge. So it's like there's a big amount of steps that make this work. That's why it does this. That's why it's so low energy, and that's also why the energy that's captured is put back into it. Because you need a decent amount of energy to do it. Kind of, yeah. I mean, for what it is, yeah, kind of. Like I have batteries. So for what it's worth, like I have an alternator, I have a battery, and then I have another alternator, generator, and then it's like it eventually will get hot enough and it'll continue its production of this that it'll have too much and it'll go into the third and final thing that I have, which is a static charge, kinetic static charge, kind of like static, headphones, where they're like static electricity headphones, so like they move. I forget what the hell they're called right now, but the point is they use static differences, charge differences, to move a thin membrane to then produce sound for us. You know what I mean? They call it an energizer instead of an amplifier, which makes kind of sense, but then kind of doesn't. Anyways, it happens to be really rather weak. But when done properly with the right materials, when you happen to dump the electricity into electromagnetics, meaning coils that are around that, phaser, no. Come here. Come on. It produces a alignment of magnetic poles to these static charges that are already heading that direction alongside of the rotation of that direction. And so the electromagnetic also happens to produce its own repulsive force, while the static charge happens to produce a kick, a hit, an impact of a direction as it moves. And it's still going to attract itself, and then it'll go into and then produce a kinetic change, meaning alignment with the other electromagnetics. So we have a bunch more phases though. So it's like 12 phases effectively are there. Instead of 3, we have 12. You have to have 12 for this, and you have to have the right material that uses static, and then you have to have no magnets. There's no magnets, it's just electromagnetic coils that have to be aligned properly and effectively coiled properly too, to allow for the material, as the static charge differences dump into each other, it then aligns itself and then pushes the kinetic change instead of opposing and towards each other towards a direction, meaning side, in the same direction that it's traveling in terms of its rotation, meaning counter or clockwise. Okay? Which gives it a great, and I mean massive, degree of increased significance in terms of actual energy input into the electric motor. It's all about the materials, it's all about the pole alignments, and it's all about the electromagnetics and the switching and the phasing and allowing for it to get close enough to dump the energies from those fields to make that change, kinetic change, occur. So there's a lot there. Phaser! And god damn it, give me a second. My cat claws his face and he doesn't even fucking flinch. It is disturbing. Like, for real. Like, she's like, I'm gonna boop you with my claws. He's like, whatever. I'm just seeing her trying to take the claws out, and I'm like, Phaser, that is not okay. You need to not go after the cat. Can you stop? So, like, there's that. Anyways, I gotta get the bed sheet and the other stuff going. But this is laundry time, so you might come with me to laundry. You might not, because it's Sunday. It is June 14th, I think. June 14th. What day is it? God damn it. What day is it? I think it's. Give me a second. No, it's not the 14th. We are the 16th. 18th. That's what it was. 18th. We're in June 18th today, so that's what that is. Sundays are laundry day because it's cheaper. I just feel like having some semblance of a routine, considering I don't really ever have a routine ever, and it kind of sucks because I'm like severely ADHD, and like I can barely focus even with Vyvanse, and I need to talk to my doctor. None of them have wanted to talk to me or anything for a while. I've gone through like all the ADHD medication, and like I've done all the medications for like SSRIs, SNRIs, tricyclics, tetracyclics, mood stabilizers. This just keeps going on and on and on and on that side. Like it's like I've gone through all the meds. The only thing I haven't done is benzodiazepines. Like even done like non-stimulants, which my parents will disagree, but I remember. Because it's like, oh yeah, I'm going to tell them that I have these thoughts and feelings while on this one. Well, if I do the same on this one, they'll send me back to the place where I'm not allowed to go home again. So that one turned into, oh yeah, no, I'm super psychotic and paranoid, and I don't sleep on the non-stimulants. And then I sleep way too much, but I'm super aggressive and depressed all the time. Like super depressed all the time. And then I also have shitting issues. So that one's nice. It's like, those are atypical side effects. You'd never experience that. And I'm like, well, I'm one of those dumbasses, which isn't a dumbass, that happens to have rare side effects that sometimes aren't even on the label. But they're still there if you really look into the literature for like the percentages that seem to report something like this happening. And so that's like the reason why I have so many different, because I've done EMDR, dialectic, cognitive behavioral, executive functioning therapies. Doesn't help as much. I really just need a person, for what it's worth. But like, no help coming there, My therapist is kind of shitty. Anyways, where is this going? Basically, it's an electric motor that you have to have both sides work on, and that's our clutch and flywheel package, which we have a flywheel that disengages with some gears and clutches as it spins to a certain speed, and then that way you don't need that parasitic weight that's there for compression, because it's not necessary. So it gives you a faster rev, and it'll re-engage. You know what I mean? So it's like a really good way of going about. You still have the parasitic loss in the engine, but like then it's not for the flywheel. So it's like, that seems stupid. Why would you do that? Because it's like, well, you wouldn't manufacture it because it's too expensive for you. But if we're upgrading this and we're going to upcycle that, it's like, well, I'm going to sell you this, and it's going to make it so that way you get gas and or diesel that works way better. Far, far better now. To the point where the efficiency is massively increased for what it's worth, and also improves the particulate, meaning pollution, that comes out of both engines. And so it's like, that's why you would do it. While improving its outright performance as well. So it's like all the things that you would do. You know what I mean? Like if you're having like we need to make these things last, and we need to make them work, and we need to make them run very efficiently and well, while we transition to an infrastructure to more renewable. Which I still have plans for that one, because that one will take its own sweet fucking time. It's like, well, you know what? This one pot method and everything, which is really just dumping fecal matter, plastics that can be broken down, various other junk like asphalt rolled bits, stuff like this, rubbers, carbons, that, and it's like, well, using the right bacteria, and then using the right mold, and then using the right fungus, and then using the right heating and pressure, meaning as we vibrate, but then we also use IR, laser kind of things. We then create pockets of extreme heat that break down under the right pressure, the plastics more readily without having to use as much heat and pressure, and we have water still in there. So that's a catalyst, but then we have also all the other stuff that's in there that can also act as catalysts. So then we get natural gases, and then we'll get fuels, like gasolines, ethanols, and fuel oxidizer compounds alongside of regular diesels, because there's oils there too. And it's like, well, that seems really rather efficient. It's a long term. So it's not I can brute force, billions of gallons in a few days, unless I have the right scaling of the pots and everything put together. This is more of a, well, added to our current infrastructure for waste management, for clearing forests, so less wildfires, for removing this dead waste from farms, and throwing out organic material and matter from grocery stores, alongside of our waste dump sites and plastic recycling refineries, which they can't recycle everything, turn into this. Now becomes a viable, greater than the energy put in, using renewables, solar, wind, and some algae production that will go into making this a very viable fuel source. That's cleaner. It sinks carbon. We have to separate some of the energy, with energy that we have to separate some of the compounds, not energy, into different, useful, viable compounds. Because there could be heavy metals, there can be metals, there's definitely going to be sodiums, which are batteries. And some of those are also for lithium's batteries, so people take lithium as a medicine, and it doesn't get filtered quite as well. And we also have golds, and so a lot of that's there, and it's small amounts, but then when you scale it to the size of the United States of America, it's not as small. It's a really good recycling process that produces fuels that you will run, alongside of a hybridization of our current use of vehicles. because we already have now, with this upgrade, well, we have an electric motor. And that's also a generator, technically, if you want to put magnets in it. But you don't need to. Otherwise, it's just a regular electric motor with static charges. But those static charges, yeah, see this one? If I put the right reduction of electrons, that's a grounding, and then if I have the right material, I have a magnet, and then I gain a electric motor. That is correct. That is also a generator. We were going with generator, okay? Just so anyone out there is wondering, that's a generator. It's like electric motors. Oh, it's a generator. That's what it was. That's what you were thinking of. It was a generator. Yes, we get it though. Like they're kind of the same thing. For what it's worth, they're not much different. It's one of them you're putting energy in, the other one you're taking it out. So that's effectively why everybody kind of gets confused on it. So that's what's there to a point. You know what I mean? It's a clutch flywheel package that's a static electricity, static kinetic electricity, and electromagnetic field generator motor, depending on the materials and everything that you use. So, and it's going to need to be ceramic, and it can't get super, super close, and so eventually it will fade. But then you can just replate it with ceramic, or recoat it, really, and then it's back to the races you go. It's just got to be brushless and brushed. So like there's brushless and brushed together on this, because you have to have the phases, and you have to have it on the outside of the housing and on the inside, and then there's the axle that it's connected to, which has to have the brushed but also static connection points that it runs through as it rotates. Okay, which means you can upgrade engines dramatically, improve power, improve efficiency, and significantly reduce emissions while making it within the scope, especially if we run subsidized government programs to upgrade the fleet that we have, meaning all the cars and engines in our existing infrastructure, not just for commercial, but for civilians. We gain a significant reduction of overall fuel use while improving air quality by a good amount. Then that allows for us to transition over to a more renewable, hybridized infrastructure of the two, and use batteries that we gained from these sources of renewable, mining, basically, operations from these one-pot methods, creating the fuel, reducing the fuel overhead, on these companies that may or may not have issues at times producing enough, reducing our reliance on fossil fuels that are foreign, and now we have renewable fuels that are within our own country, national, within our own state, within our own county. Like, that's what that would be. It's a way to treat waste. And it's like, well, the government's getting in my private corporation that oversees my waste management, my fecal, our sewage, and our electricity. And it's like, well, there's going to be extra, and there'll be fertilizer, and it'll go over to your farms that can just topsoil layer that, and it's a bunch of carbon that they're going to love, and you just got to layer it. But the thing is, it's like, well, this is a program that you only get if you happen to do the method of plowing that doesn't break up and till your land. Instead, it lifts it up and then it closes it back and allows the root structure to still be there. So you can place the seed down, and it allows for carbon sink for all this fertilizer that's on top, that as rain comes down, it'll sink down, along with nitrogens that are still going to be there, along with all the minerals. You'll still have vitamins, because, no offense to anyone out there that might not know, but fecal matter and, urine still has vitamins and minerals in it. And you can just keep that there. You don't want it for your fuel, is what I'm trying to tell you. So that's going to go right there into all of your crops, making them more robust, or nutritionally dense. I can't promise that the rain will still rain and the sun will still shine, but I can tell you got good soil. right? But of course, elephant in the room is all that costs money. Like, how much is that really going to cost? And it's like, well, not as much as you might expect. Most of the material's already there. Most of this is a stamping process. Most of the way that we're going to stamp it already exists. The one-pot method is effectively a refinement of our current hydrothermal process. That's a pyrolysis process, which uses the machinery of bacteria, mold, and fungus to make more starches and or make more hydrocarbons that are more ethanol-based or other types of, fuels. They're not really going to be a gasoline type most of the time. If I'm going to be really honest, it's mostly diesels and ethanols that will then be attached with a degree of a fuel oxidizer. And so that means less air that you need to intake for the given amount of power that you want to receive. So you can run leaner because it'll burn cleaner. And then whatever you didn't, you've got a really good, solid catalytic converter design, very efficient power platform that can still be hybrid by allowing for sodium ion and lithium ion battery packs together. Okay? Until you can transition to a cleaner, material, which is better for the environment. And so we'll start carbon sinking faster because we're using less energy to improve our vehicles. And yes, while there is an initial investment, our existing infrastructure can handle this alongside of that going together. And then it can really start transitioning to greater and greater degrees of renewables and lower amounts of fossil fuels and even renewable fuels. Because our technology will catch up to the point where it's reasonable to expect solid-state batteries and these new, electromagnetic static charge kinetic motors to be on the market, right? And then I still have my battery generator as on YouTube and stuff. So, that's the reason why I was thinking about it. It's like, well, we can't have the best of both worlds. And truthfully, transitioning is hard. It takes a lot of effort, it takes a lot of time, it takes a lot of money, a lot of resources. And it's really hard to get someone to change. Well, this is a way for them to slowly have that there while starting the process of carbon seeking very soon. And recycling very soon. And renewables becoming much greater in terms of their parts of the process very quickly. Which is a better option because it means it's more likely to be taken seriously and used without needing all this plasmification, although I still have it technically. You know what I mean? It's one of those, well, why wouldn't I do that? Why wouldn't, I can put water instead of fuel in there. There's nothing saying I can't do it. That's water injection now with plasmification. That's like steam. It's still going to give me power. So I use a little bit of hydrocarbon and I can scrub it out after. And that's less fuel now. It's like, why don't you do that? And it's like, well, for what it's worth, I do and I don't. It depends. You know what I mean? It's like you got to do a different kind of intake and exhaust, and you need to reroute that carbon back into the system. I used a graphite carbon nanoparticle design that happens to inject that with a air pressure injector, kind of like a methane injector, that then sprays it as a fine particle with a little bit of water to reduce static. And then as it goes up to top dead center, and then it's already burning, and then I basically create a plasmification of water, and it'll recombine as a super critical steam that burns any leftover stuff that then will also slowly exothermically react because it'll typically decompose as it crashes out, and they can add in a little bit more water and then it'll stop decomposing, but then it also breaks down exothermically a lot of that other, and so it gives it more cycle time. So it's instead of a in and out, 4-stroke, it's more of a It goes in, it presses, it does it again for another in and press, and then it does it one final time, and then it at bottom dead center opens up near bottom dead center and all the way to bottom dead center, and then it starts the process again with a little bit of leftover steam and hydrocarbon and all that to then start the process again as a increased degree of torque and increased degree of RPM, because I'm maintaining torque and I'm maintaining thermal efficiency, and you won't notice the difference. But it's a very, very, very different sounding engine. That means people probably don't like it as much. But the amount of torque is very high, and the significant reduction of carbon is extreme. Like, I effectively capture all the carbon I'm using, and it's usually water that I'm really just burning. Like, I'm not technically burning water, but I'm going to waste water. Like, water's now the fuel that I slowly run out of, for what it's worth. You know, and the catch can is no longer like an oil catch can, it's a percolator water catch can that helps reduce some of the heat of the steam, because I don't really need the catalytic converter. I just need to separate the carbon, because most of the time the carbon will no longer form to the oxygens, because I get peroxides. Peroxides will then break down into H2O and O2 respectively. And so the carbon tends to try and form into nanite particles, you know, graphite nanite particles, which then makes a really, really good lubricant, but it also means that that is like going to go into our atmosphere in the steam, which typically will rain pretty quickly. But if I capture a good amount of it, then it's like, oh, well, I gained the vast majority of my fuel back, so, you know, I don't really need to top up on fuel for a really, really long time. It's really just water that I need to top up on. Right. And I need batteries to start the process off. So, like, batteries are really a big deal for what it's worth. Like, batteries are the big, big guys. And alternators. And so, like, I create the plasmification, and then I have to have transformers and, you know, all this other stuff. So there's a lot of electricity stuff happening to make this work. But at the same time, once it gets up with enough heat, then it becomes a lot less of that electricity, and it's more of the heat that helps it as it compresses and maintains its torque. It increases its efficiency, really reduces carbon dioxide, monoxides, nitric oxides, and other particulates out. In fact, they're basically non-existent. There's still going to be some, but there's effectively almost none. Now, the amount of electricity use at first, for people that don't know, might expect that it's very, very, very high. Like, that's what that would be, right? It would be super high. But it's like, not really. It's more of a grounding effect, and then voltage effect, and then like a negative charge. There's like a lot of really fast electricity changes that we're going to have to add in that are only going to be useful at moments, meaning certain moments that then create the effects that we want, and then it'll continue so long as the heat is there. So the heat is what really we use, which means there was a significant reduction of electricity, but we still gain steam, you know, and a lot of exothermics, because exothermics are what's really making it maintain its degree of pressure and outright power. Turns out exothermics, chemicals, are really good at reforming and then, you know, disconnecting, and through that exothermic process you can gain some energy from it. Now, the reason why I only do 3 is because the first one, it's like pretty good. The second one, it's like I still get a little bit. It's basically nearly the same or slightly above, depending on the process you use. And the third one's basically 80%. Like, it's like, take 100, you might get up to 105, you get a really good process and stuff with the right materials and so on, and then the next one's 80%. And so it's like, gotta get rid of it. Like, you can't keep pulling energy out of that. So it's like, there's exothermics, but then eventually the exothermic reactivity that increases heat, and we dump more water in to improve the density, and as a result the pressure, to improve its degree of power and torque as a result. then we lose after. So it's like we're taking energy and we're putting it in. But because the energy to put more water in is less than it takes to, make that water turn into steam, because there's already a copious amount of energy there to make it steam, and there's already a copious amount of energy there to keep it going, instead of trying to plasmify it, and as a result, it's like, oh right, we don't use as much energy to make the same amount of pressure. In fact, way more pressure now on the second one, but you get close to it. And so that's why it's like 105. It's not really more. You're getting slightly more. You know what I mean? For the given energy you put in, you get slightly more because of exothermic reactivity. But then you don't get that back on the third one. And you get near close to that. But that third one really just removes carbon. It crashes it out and precipitates it into graphite. It's like, you don't. I don't know anything about this. I don't know why that would work. I literally don't know the materials. I don't know anything. It's like, why? And it's like, well, there's pole alignment. There's, static charge differences. There's, the right material coating, which helps form more styles of peroxides versus not. It also uses carbon as its form of catalytic conversion, which is its own version of a grounding / as it dissipates outwards into the surrounding cylinder and the rest of the head, which the electricity has to go somewhere. So it's like you have to do that. And so if you're a person that might be intelligent but doesn't know everything I'm doing, you might go and say something stupid like it can't be done. And believe that you're smarter than I am with making this happen. But that's why I say that. Because it's like, you're not. I know what I did here. I know how to make it work. I know that there's very specific material that's very good at helping form peroxides, and they're not even expensive. I also know that there's a lot of good material, ceramic-wise, that will withstand that effect, especially when there's already heat and pressure and electricity being involved, which are also conductive in the right ways. Which then also means I don't need as many electromagnetic and static charge and all these cables and wires and doohickeys for rectifiers. And in fact, I have a capacitor difference effectively at one side versus another that allows for a drop in voltage, and so it in its own right stores its own type of electricity, which goes into reheating and plasmifying and so on, making it far more energy viable, because I get more energy out by just simply adding a little bit more water instead of carbon, And then the third is like, well, I'm basically using that static charge and all that's there. It's going to be there, again, on the fucking next power stroke at the top dead center, compression and power, as a result of doing that. But that helps dump carbon into graphite. Okay, so it's like that graphite is then recaptured, and for the given energy it takes to recapture, that I got out of simply, not capturing the water, I gained back way more. H going into O is less energy than C going into O. And so as a result, I'm very efficient at capturing C into O energy and turning H into O energy during that process into making it so I can recapture the carbon and keep the process going. Now, I don't capture it nearly as much. It's not 1% anymore. It's like 99%, for what it's worth. It's like I get like 99% with a good oral catch can. There's some static charge differences, that kind of thing, with exhaust manifolds and the heat and the little valve and all that, which then eventually gets to the point where I have to go through a filter, and as air goes over, it then dries it off, and that captures some of that into the intake, but then that also means it filters it like a sieve until eventually I grab it into like basically a version of a pressurized fuel rail, which is really just a cylinder that goes off with a flow regulator and pressure regulator into the methane injectors, which are just going to inject this graphite. So it's like there's a whole bunch of steps, and I have to pump it. All right, but like pumping is not as hard when it's a slurry, for what it's worth, you know. And so that makes it a lot easier and a lot more viable because tubes can be made to do that. It's a lot less energy intensive than trying to like do something else. Plus, for the energy I use, I'm traveling down the road. I have a very large amount of torque, like an enormous amount of torque. For what it is, it's like I actually have a good, pretty serious amount of torque. Diesel is less torque happy than this engine built. Because I have 3 power strokes effectively before exhaust happens. You know, which is sustained with exothermic reactivity as it goes down to bottom to center, which means I have a lot more torque than a diesel, and it's way cleaner. Which, like, if there's an engineer out there listening to that, it's like, oh yeah, no, you would actually, yeah, no. There's still the compressor, you know, and then I have the ram air, and then I have the turbine, which is going to help separate some of the carbon graphite material, you know, right, yeah. Right, which makes it more efficient, and then all the rest of it that I talked about, because why wouldn't I do that? And then I'm like, well, I can still put it at the bottom, you know, I have a top and bottom combustion chamber. Nothing says I can't do that with like a straight piston and the right seal. You know, it's just water anyway, so it's like was it not hydrodynamic, hydraulic fluid, which is water-based, which is a lubricant, but then can still go into the piston rings and still be a viable help in terms of helping the seal, because like in the plate that's going to be straight, that just has piston rings, you know, opposing, you know, gapped piston rings with tapering, you know, so in like a star or like an asterisk pattern. So that way it allows for it to increase the surface area, and so I increase the surface contact area. I don't really care. To be fair, I really don't. For me, it turned into, well, I actually really significantly decrease the ability for that air to travel to the bottom. Now, the bottom part has a, you know, column of stuff that's there. Well, I also increased its surface area, well, lessened its overall volume, and still increased its strength and rigidity. But as a result, it also means I improve the amount of air and fuel that's burnt, which is really just water. And so it's much closer to the top. It's not the same, but it's very close. It's like, well, I could probably get close to the 85, maybe 89 out of the top. You know, 0.89, 0.85 of the total volume of the top, which is not bad. As a result of this, I gain a measurable increase in torque, like huge increase. Like I already had more torque than a diesel, regardless of how it was set up. Like I have a shit ton of torque. I can really put torque down. But then it's like, well, so I felt like that wasn't enough torque. So I said to myself, what if I nearly double the torque? Which it's like you can do, but you're probably not going to, because for a consumer car, it's not in any way necessary, and that one just turned into a double crankshaft. For what it's worth, it's like it has a connecting point where it's you know, connecting rod is to then bifurcate into 2 crankshafts, which is easy enough to do, and it's kind of like an accordion. As it goes down, it'll go back up, and so it's like it's not going to go past a certain point, and then it'll go back up, and it gets pulled up, it pushes up, that kind of thing. So you just have to connect them the right way and have the right spacing with the right little connecting where the wrist pin, because that's its new version of wrist pin, effectively. So then you have a crankshaft, or crankcase, vent, same thing with the top. You still have to have it at the bottom too, which allows for that to get sucked into the compressor through the hydraulic fluid catch can, which allows for you to have your spinning valves, which allows for the hydraulic fluid to really do their work, because there's a place for a shaft, and there's nothing saying I can't effectively do that. Now it's going to be a different style. Instead of like a shaft that's like that, well, now it's more of a donut ring. So there's a way to do it, and as a result it's like, well, I've got even more power, and I'll just have the exhaust go into the bottom, and I'll keep the exhaust, and I'll just use less energy to help the process of the compression in the next one, and I'll get even more torque for the given amount of energy that was there put in. Why not, right? I don't have to use as much carbon for the bottom. As a result, I've gained more efficiency and more torque and more RPM and more horsepower, and I'm way more efficient and way better in all the ways than any gasoline vehicle with my steam engine, internal combustion steam engine, which it's combusting, and it's steam. There's a caveat with a lot of electrical internal combustion steam engine. There's the caveat is there's a lot of electricity, and there's batteries that we have that can make that work just fine, and it's going to be a hybrid anyways. So you know what I mean? Like, I don't really see a problem. I think the right alternators and the right, instead of like, oh, I'm going to have like this turbine to the catalytic converter, it's more of a turbine to like the right little, just drain all that heat into the thermal siphon part, and then gain that energy back, and help the process of the engine do its job, and then dump it off into the catch can and slurry it all up, and you get a lot more of the energy back. Now, the only reason why it works is because of the electricity. You can't do it with just graphite nanoparticles. I mean, to a point you kind of can, but not really. Like the hydraulic fluid, which is a lubricant, definitely helps us out, because you're going to burn a little bit of it, but not much, for what it's worth. You know what I mean? And then it's like, well, now I have to drill into the sides to push in hydraulic fluid to the piston rings, and then have that get sent out the other side where it's the receiving valve. So it's like those are, ring valves as they go through their version of middle dead center and keep getting lubricated, and along with the pressure helping push that fluid back down into the sump effectively. Which actually I don't use a sump. If you don't know, I kind of do, but I have a box of hydraulic fluid that's always full, and then that just drains it off, and I'll pick it up if it ever gets low. But that way it like pushes the fluid off into somewhere else, and it can cool it, and then it can push it back into everywhere else it wants to go into. So that way you don't get bubbles and vaporization and so on. So it maintains its efficiency. So, anyways, finally done. Bye.